Good morning. Um, Casey, right. You guys doing okay this morning? Yeah? All right. Let's see. For your clickers soon, maybe today or maybe on Friday, I'll post sort of where I have you as your clickers, like the clicker ID that I have for you. And then if we have any points, which we will by that time, I'll post what I have just to make sure that we're all on the same page. So if you're not yet registered, I'll put the class roll registration, and I might actually go ahead and send out an email with sort of who I don't have registered, so you can send me your clicker ID. But if you haven't registered, don't sweat it. Just use your clicker today. You have any questions about what we did last time? Mainly just did sort of orientation stuff, but any questions? No? Listen, there were some glasses that were lost in the class last time. Anybody pick up a pair of prescription glasses? Okay. You know the secretary? She's just right over here. All right. So that's good. Thank you, Desiree. Yeah, that's very nice. Okay. Let's see. Remember last time we just started on standards? You'll see some multiple choice questions on your test about standards. Remember, standards, in order to be good standards, they need to be accessible to everyone, they need to be accurate, and they need to be unchanging. And the reason that the kilogram was not ideal is for what reason? What is it not? The kil It's changing, right? That's the big thing, really. And then also, it's not really accessible to everyone. When you have this physical object that represents the standard, then that's not accessible to everyone. So the big one is that it is changing. It's changing mass, in fact. And a secondary reason is that it's inaccessible, not accessible to everyone. That's not such a big deal because they made these copies, right? And the standard that they're trying to move to, there's some other options, but the standard that they're trying to move to will be based on the mass of a silicon atom. So what they're trying to do in constructing this sphere is that they're constructing a sphere that is a kilogram based on what we currently know of as a kilogram, and then they're going to count the number of atoms in that sphere, and then they'll say X number of silicon atoms is 1 kilogram. So now we'll have a standard that's based on the mass of a silicon atom, which we can measure, which we know. So the movement now, and the kilogram is really the last one to move to this standard, is to have all of our physical quantities based on a physical constant, like the speed of light, like the mass of a silicon atom, or as with time, based on the frequency of a cesium atom. So the current measurement for time is the what? What's right? So we're in the MKS system. That's meters, kilograms, seconds. Chemists, astronomers sometimes use the what system? Said this last time. CGS, right? Centimeters, grams, seconds. I don't know why, but that's just what we use. So the current unit of measurement is the second. You know what a second is, right? The standard used to be based on the fraction of a solar day, some fraction of a solar day. While that's accessible to everyone, it's not very accurate. Especially now when we have a lot of wireless communications and we need to know time very accurately in order to process those properly. So now we have a second that is based on the period of a cesium atom. It's defined as 9 billion times, roughly, the period of a cesium atom. We're not going to get too much into it, but you can cause the cesium atom to vibrate at a very regular frequency. And you just define the second as a certain number of those vibrations, about 9 billion, not exactly 9 billion, but just for reference. Okay. Oh, here's just a little hint. If you ever need to know the number of seconds in a year, who doesn't need to know the number of seconds in a year, right? It's about 3.14 times 10 to the 7th. So how many seconds are in a year? 3.14, what is that? Pi, right? So the number of seconds in a year is pi times 10 to the 7th. And your friends will be impressed if they ever ask how many seconds are in a year and you know it right off the top of your head. And now you know. All right, so why is it important to have good, accurate standards to measure, and what are the qualities? We've already sort of addressed this, but it's important to have accurate standards simply because, you know, that's how we measure things. In fact, people all throughout history have had standards. Back in Babylonian times, they'd use a lot of sort of, like they'd use their foot, for example, or they'd use a certain measure of seeds as a standard for mass, and that's how they measured things. And so in a similar way today we have standards. So it's very important to have standards because it defines what it is that we're measuring. And then also the qualities of a good standard: accessibility, we've already written these, uh, accuracy, and what was the third one? Oh, unchanging, right. All right, let's try a little quick test question. Which of these is a reason that a standard of measurement rather, is not appropriate? So I give you four options. It's one or more of those options. This is a reason that a standard of measurement is not appropriate. The standard changes. The standard is not available to everyone. The standard is based on some obscure physical constant, or the standard smells really bad. Which of those is a reason that a standard is not appropriate? This is in your workbook if you can't see. Standard changes. It's available to not available to everyone. Is based on some obscure physical constant, or the standard smells really bad. All right, doing very well. Let's do about 10 or 15 more seconds. You have your clicker going, click in, okay? Remember these questions that we ask in class, these go towards the class participation part of your score. You can get up to 50 points in that. I'll give you a little bit longer while you get your clickers out. All right, I'm going to stop at 125. 125. Oh, very good. Excellent. The right answer is E here. The reason for these be inappropriate would be if it was changing, like the kilogram is, or if it's not available to everyone, also like the kilogram. It doesn't matter if it's based on some obscure physical constant. The other two, they're based on some obscure physical constant, right? The mass of a silicon atom, who cares, right? The frequency of a cesium atom, who cares? Those are pretty obscure, and it doesn't really matter how it smells. Hey, Thomas. All right. You will need to know your metric prefixes. You've probably seen these before. If you haven't, you're going to use them a lot as chemistry, geomatics majors, and what have you. Uh, there are some ones, actually, these are all ones that you'll need to know. Nano, micro, milli, centi, kilo, and mega. Nano is small because it's like nano, you know, like nanotech. And it sort of looks like 9. If you replace the A with an I and the O with an E, it would become 9. So it's 10 to the minus 9. And then it proceeds by threes. 10 to the minus 6 is micro. Milli is 10 to the minus 3. Centi is sort of an oddball. It's 10 to the minus 2, but we use it a lot. We really use it in length measurements like centimeter. A centimeter is 1/100th of a meter, or 10 to the minus 2 meters. And then we cross over. Kilo is 10 to the third, or 1,000. Mega is 10 to the sixth, or a million. And then giga is 10 to the ninth. Or as I learned on Electric Company, which is one of my favorite shows, that giga, when a G is followed by an I, Y, or E, it makes a soft sound. So it should be really giga, not giga. Did y'all know this? So now when somebody says gigahertz, then you can say, no, 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 no. It should be what? Gigahertz, like gigantic. All right, so those are our metric prefixes. We'll use dimensional analysis, or excuse me, we'll do a lot of conversions with these throughout the semester. We'll have some practice with it in this chapter, but you'll need to be able to convert between the different metric units as well as different systems of measurement. All right, so we'll see this in a little bit, but you'll need to know these. I will not provide them for you. So if you don't know these right now, you just need to commit them to memory, okay? Because you'll use them this semester, next semester, and in other classes as you go about either as a chemistry or geomatics or even biology. We'll see those. Okay, dimensional analysis is also something that we'll use, and we'll use it just sort of as a separate topic in this chapter, but you'll see it throughout the semester as you work various problems. You've probably done this before. Dimensional analysis is just where you look at the units of a problem, and often scientists will often just look at the units and try to get the units to work out right, and then they think they're pretty close to the answer. So it's a pretty useful tool to just see if you're going on the right path, because if your units aren't correct, then you're obviously not doing it correctly. Uh, First, before we work through some samples, let me just give you some common dimensions and units. I think you know this. Area in the MKS system is what? Meters squared, right? Volume is meters cubed. Velocity, right? Meters per second, or speed if you want to call it that. And then acceleration is very good. Those should be pretty easy for you. So those are the units. And now we want to test some equations and figure out if they're dimensionally correct or not. So I'll do this first one for you, and then you can do the other two. I have x equals vt. X is in meters. I'm just writing in the units for each variable. V is in meters per second. And then t is in seconds. And then I just cancel out all those that cancel. So here, my seconds cancel with my seconds, and I'm left with meters on this side and meters on this side. So that equation, yes, is dimensionally correct. It just means that the dimensions on one side match up with the dimensions on the other. All right, I'm going to give you a little bit of a head start on B, and then I'll work it out. And then on C, we'll do that as a clicker question. All right, here, just a couple of things though. The 0 here, we usually say this is x naught, and we use this a lot throughout the semester. Anybody know what the 0 means? It's the starting point. It's usually seen as a 0, and it means at t equals 0, which we usually take to be the starting point. So it just means the initial position, or the initial whatever it is that you're measuring. And then also when you're doing these dimensional analysis, anytime you have a constant like this, it has no dimension, so you just leave it out. Don't even worry about it. All right, so does this equation, is it dimensionally correct or not? Just write out the units for each one, cancel out any units that do cancel, and then if they all match, then it is dimensionally correct. About 15 more seconds and I'll start doing the answer. All right, x is in meters. What is x naught in? Meters as well. V naught is meters per second. T is in seconds. Don't worry about the 1/2. A is in meters per second squared. That's acceleration. Usually when we represent area, usually for area we'll give a capital A. But A here is acceleration. And then t squared is seconds squared. Is that equation dimensionally correct? In order for it to be dimensionally correct, all the units have to be the same. So I have meters here, meters here. I get rid of those seconds, so I still have meters here. And I get rid of those seconds squared because they cancel out. And I'm left with meters here. So I have meters in every term. Meters, 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 meters. So it is dimensionally correct. If I add up meters plus meters plus meters, I still get meters, right? 2 plus 2 plus 2 meters is still 6 meters. All right, let's try this one. And I want you to answer this as a clicker question. You can go and start. A will be yes, it is dimensionally correct. B will be no, it is not dimensionally correct. If you finish this one, you can go on to the next page. We're going to do that as a clicker question as well. Right, I'll stop at about 110. That gives you about 20 seconds left. It's 5 more seconds. 5 more seconds. Okay, awesome. B is the right answer. This is not dimensionally correct. Look, I have V as meters per second. I have A as meters per second squared. That's acceleration. And anytime I have one in the denominator like this, I write it as 1 over seconds. That helps me to think about it a little bit better. You can write it how you like. Uh, plus zero point 0.5, I leave that off, and then I have meters and I have seconds. So here I have meters per second, here I have meters per second cubed, and here I have meter seconds. So that is not dimensionally correct. So if you have an equation and the units don't match up like this one does, then you know that it can't be correct. Let me go back. I forgot to give y'all something for these metric prefixes, and those are the letters that represent each prefix. I'm sorry, I just looked at my notes and realized this. So the letters that represent each of these prefixes, you probably have seen these before. The first is nano is N, micro is the Greek letter mu, milli is M, centi is C, kilo is a lowercase k, and then mega is an uppercase K, and giga is usually an uppercase G. All right? Got those okay? We'll see these throughout the semester. So we'll see them again actually in this chapter. We'll work with them a little bit. Y'all know your metric prefixes pretty well? Or you've seen them at least? Familiar? Okay. You'll need to memorize them. Just make sure you know them in that order. There are a bunch of other metric prefixes, but you don't need to worry about those. All right, let's try this quick test. This one's a little more challenging. Here I give the units off to the side. V should be meters per second. Be careful, this M is not meters, it's kilograms. It's a variable here, so you'll need to replace it with its unit. So is this equation dimensionally correct or not? A, yes, B, no. Just a little trick on this. If you want, before you write in your units, you can cancel out things. Like, so for example, I see here that I have an M and an M on both sides. I can just cancel them out before I even write the units. Similarly, I have an A and an A on both sides. All right, about 15 more seconds. So go ahead and finalize your answer. I'll stop at 210, 210. If you do really well, I'll give you a joke. But unfortunately, I don't think we're going to get a joke on this one. Sorry. All right, 212, I'll stop. All right, looks like we're sort of split between A and B. Let's just try this out. Remember, like I said, you can get rid of some of these. I can get rid of my M's here. I can get rid of my A's here. That makes it a lot easier. Look, I can also get rid of this V with one of these. So I'm just left with this. So looks like I'm left with meters per second on this. That's X over T equals V, which is meters per second. So is that yes or no? A is right. All right. Listen, guys, there's some homework problems having to do with these, and if you look back at the old test questions, you'll see some extra practice. I recommend that today and as the week goes along, that you work through those problems and just make sure that you're up to date with it. We'll have 5 to 10 points on the exam just based on this, so hopefully those are gimme points that you can just get them right off. But I realize that some of you are having trouble with it still, so I'd recommend we'll see it a little bit more, and I think it'll sink in. But I'd recommend that you start looking at that homework. In fact, you know what? It's a good practice for you guys every day to set aside 30 minutes, at least 30 minutes. Oh, goodness, bless you. At least 30 minutes for every class. All right, really, you need to be spending about an hour every day for every class, but I realize that's probably not practical. So, don't watch whatever it is that you watch for 30 minutes and study physics or chemistry or whatever it is you're taking this semester, okay? 30 minutes to an hour every day you need to be spending on your classes. All right, let's see here. Let's look at uncertainty. Uh, some of you are in lab. We sort of deal with this a little bit. The uncertainty of a measured value depends on the method of measurement. It just tells you how well you know a value. Just how well is that measurement been made. So say, for example, I have x equal 4.5 to 0.2. X potentially has a value anywhere between two values. What are those values? Right, 4.5 minus zero point 0.2 and 4.5 plus zero point 0.2. So anywhere between 4.3 and 4.7. Now we'll sort of assume that we have an equal probability. That is that our probability can be anywhere between 4.5 and 4.3 and 4.7. But in reality, don't write this down, but in reality, often it's the case if I were to plot the probability versus the value. Don't write this down because you're never going to see it again, none in this class. The probability really looks something like this, where it goes between 4.3 and 4.7. So it's most probably at 4.5, but as you step away, your probability that it is one of those values between 4.3 and 4.7 decreases. That's a whole course, and some of you might see that in some of your other courses, like quant. Maybe I'll do this in quant. I don't know, but in some of your more lab-intensive courses, you'll get into error analysis and uncertainty and what have you. So you'll see that again. You also see sig figs. You did this in what? 5th grade? Significant figures? So, right? 5th grade? 4th grade? 3rd grade? 2nd grade? Okay, you've done it before, right? Sig figs? In fact, let's see, a significant figure is just a reliably known digit. We often call them sig figs for short. But we could also call them what if you're in my lab? What did y'all start calling them? Sig digs, right? Because significant digits. And so instead of abbreviating figures, you could abbreviate digits. Sig digs. That's a lot cooler, I think, than sig figs, right? Is that more cool? Yeah. All right. I'm not going to go over the rules, but I have a little video, and this guy just covers the rules for significant figures. So let me just show you that, and then we'll do a few examples. I think that's probably the best way. Have y'all seen that one? No? It's on YouTube, so you can show it to all your friends. Put it on Facebook or whatever. All right. All right, let's just go through this. How many sig figs in this first number? Everybody out loud. One. This next one? There are only two sig figs here. All these zeros are placeholders. This third one? There are three. In this case, the 0 is not a placeholder. It's actually part of the number. This one, there are four. If it's greater than if it's greater than 1 all and has a decimal point, they're all significant. This next one, 6, and this last one, 3. Very good. Now this one is a little tricky. These three are significant, the 5, the 4, and the 0. A nice way to tell if they're significant is to write it in scientific notation. And when you write it in scientific notation, it shows all the significant figures. So for example, this one, and listen, we'll deal a lot in scientific notation this semester. So if you're a little, what's the word, dusty on that, just make sure you wipe it off and that you remember. So here I would do 1 times 10 to the what? -1, right? Here I'd have 5.4 times 10 to the -3. Notice I have two significant figures here, and that's how many are in the number. This will be 1.02 times 10 to the 2. It says 1.001 times 10 to the 2. 1.00007 times 10 to the 2. And 5.40 times 10 to the -3. All right, so when you write numbers in scientific notation, all of the figures are significant. All the figures in this portion. All of the digs are sig. You know what I mean, right? They're all significant. You might see a separate problem just on significant figures, and hopefully, again, on the exam, hopefully, again, that's a gimme problem. But more likely, you'll see a problem like this using order of operations and carrying through those significant figures. So when I have a couple of rules. We did this in lab. Those of you that are in lab, everybody in lab here? Most of you? There are a few of you I know that are not, but we'll cover some of this stuff in lab. When multiplying and dividing, you use the lowest number of significant figures. So for example, here I have 205.1 divided by 2. Let's see, what do I get? If I put that in my calculator, I get what, 102.505, is that right? 102.505. But if I want to keep the proper number, can you check that, Sydney? Yeah, I think that's right. 102.505. Oh, yeah, I'm sorry. Multiplying. I was dividing. Yeah, 410.2. Thank you, Sydney. 410.2. But because I just have one significant figure here, I would not write it in this way. Instead, I would write it as just with one significant figure, as 400. All right. Here I'm multiplying two numbers, 8.25 times 5.1. 42.075. Thank you. So if I put that in my calculator, I get 42.075. What do I record this as the right answer, though? I just use 42. I just keep two significant figures because that's my lowest number of significant figures. We have a similar rule when we add or subtract numbers. We use the smallest number of decimal places, so this is rule number 2. So for example, I have 128 plus 4.7. That's 132.7. All right, but what would I record the answer as here? I would record it as 133. That's right. I keep the lowest number of decimal places. Right. So I'm rounding here. Well, I round. People sort of have different ways of rounding, but if the last digit is less than 5, you drop it. If it's greater than or equal to 5, you drop and you round up. So an 89.5, for example, is a 90. That's an A. Yay. And an 89.4 is an 89. That's a B. No, a B is a good grade. A is excellent. B is good. Okay? Oh, he has a mustache now. Okay. Anyway, that's the rounding. This is probably the type of question you'll see on the exam. It'll be a multiple choice question, just a few points. You might have up to 5 points for this on the exam. In general, you keep the proper number of sig figs for each step as given by the order of operations. People sort of do this different ways, but I suggest that you do it this way, where each time you do the calculation, you keep the proper number of sig figs. So for example here, following my order of operations, I would first do this part, and then this part, and then I would add those two numbers together. So let's see, 3 divided by 4.2. If you put that in your calculator, you get 0.714. But I would express this as what? Just 0.7, right? So I'd have 0.7 plus 2 times 6.75. See, that's what, 12, 13.5. But I would express this as what? 10 is right. I would express it as 10. So I'd have 0.7 plus 10. If I put this in my calculator, I get 10.7. But that's not the right answer. What is the right answer? 11. Because I keep the lowest number of decimal places. All right? So the right answer here would be 11. So when I'm multiplying and dividing numbers, I keep the lowest number of significant figures. When I'm adding and subtracting numbers, I keep the lowest number of decimal places. And then I just follow order of operations, keeping each step. I won't be a big stickler on this as far as your exams. I will sort of, if you're way off base as the semester goes on your exams, I might make a note of it. It's like if you have 10 sig figs where there should be 2, I'll make a note of it. I might even count off a half a point or something just to remind you. But on this exam, when you have a particular problem like this, I'll expect the right answer. You follow what I'm saying? Okay. Let's try this little quick test. Which of these answers has the appropriate sig figs? Brandon, can you see this okay from back there? Yeah. Stephen, you can see it as well? Just because nobody's answering them, I'm just going to take a couple of these options out. Nobody's giving these options, so it is either A or B. Y'all are about evenly split, I think, as a class. All right, I'll stop in about 10 seconds, 1:35. Okay, awesome. A is the right answer. I'm just going to keep one sig fig, all right, because here I have one significant figure, and so I have a number with one significant figure divided by a number with two significant figures, so I'm just going to have one significant figure at the very end. That's going to be A is the right answer. You have some other problems in your homework, and also, as I said, if you look back at those old exams, you'll see questions that are similar to this, maybe more difficult, maybe even easier. You can take a look at that and see for practice. Okay, so we'll get to some more interesting stuff. This is actually pretty interesting, but I know that you've probably seen a lot of this stuff, and so that's why I'm sort of going through it quickly. Although if you have questions, please stop me. Any questions at this point about what we've done so far? Feel fairly comfortable about it? It will get a little more difficult as we go along, okay? Oh, and by the way, I've scheduled it such that the first test has a shorter amount of time, so we'll have less material on the first test than we will on the subsequent tests, so that should be good for you. So you sort of, it's like sticking your toe in the pool instead of just jumping into a cold pool right away. That's good, right? Okay. All right, let's do some unit conversions. We'll go back and try to remember those metric prefixes and some of this. When you're converting units, you'll use just dimensional analysis. That is analyzing the dimensions of the problem in order to do this. You probably did this in high school physical science. Unit conversion? Yeah. So say, for example, I want to convert 28 meters per second to miles per hour. First of all, I need to know the unit conversion factors. How many seconds are in an hour? Oh wow, yeah, good. 3,600 seconds, 60 seconds in a minute, 60 minutes in an hour, that's 3,600. And then 1 mile is how many meters? You're guessing, aren't you? Anybody know? Who runs track? Anybody run track? No, it's not. Good guess, Shane. 1600, right. It's actually not quite 1600. It's 16 and a little bit more. 1609. Right. Four laps around a track. 1609 meters is a mile. So those are my unit conversion factors. And so if I want to convert 28 meters per second to miles per hour, I just say 28 meters per second. And then I do my dimensional analysis. I'm going to sort of write out these conversion factors. First, let's get rid of that meters. I have 1609 meters and 1 mile. This is my unit conversion factor. This is the same as multiplying it by 1, or it's equivalent to multiplying that number by 1, because 1 mile is equal to 1609 meters. You follow what I'm saying? So it doesn't really change the physical nature of this number, even though it changes the value of the number. It just changes the units. And then I can see that my units cancel out, leave me now with miles per second. And then I do the same thing for seconds. What's going to go in the numerator here? 1 hour or 3,600 seconds? Right, 3,600 seconds and 1 hour. And then my units can cancel out here. Oh, no, I'm sorry, not that. Here and here. And then I'm left with units of miles per hour. And if I calculate that, I find that it's 62.6 miles per hour. All right, notice my significant figures. Well, you're probably thinking, wait a minute, you did that incorrectly, right? Because how many sig figs should I have? Uh, if you were getting it wrong, what would you say? You would say 2, right? Because this has 2 significant figures, right? But this is a constant. So even though I haven't written it this way, this is a perfectly known number. And so should really write it as 3600.000000000, because I know it infinitely well. So it has an infinite number of zeros at the end. But I don't write it that way. I just write it as 3600. But you need to remember that when you're doing these calculations. Likewise, if you have a half or something in the equation, that's a perfectly known number. It's a constant. You don't consider those for sig figs. Okay. We'll also be converting units with powers. You could have up to 5 points on your exam, probably, doing these sort of unit conversions. But all semester you'll be doing unit conversions, because I'll give you units in one measure, depending upon what's appropriate, and you'll need to convert it back to the SI system, back to either meters, kilograms, or seconds. But I might give you micrometers, or I might give you kilometers, or I might give you grams, rather, and you'll need to convert back to the SI unit. So on this test, you'll have it explicitly, but on other tests, you'll have it embedded in other problems. It's pretty easy to do this. You set up the same tree, 5.7 kilograms per cubic meter. And now I want to convert it to centimeters cubed and grams. We need to go back and remember our metric prefixes. Centi is 10 to the what? -2. And kilo is 10 to the 3. All right. A couple different ways you can write this. Let's do the kilograms first. That's the easiest. In 1 kilogram, I have 10 to the 3rd grams. Then my kilos cancel here and here, and I'm just left with grams in the denominator, in the numerator. Now, in 1 centimeter, I'm going to do this a couple different ways. I have 10 to the -2 meters. In 1 centimeter, I have 10 to the -2 meters. And then I'm also going to have to cube this, because I have cubic meters here and cubic meters here. All right. Another way that you could write this, and this is the way that I usually write this, is instead of doing 10 to the -2 over 1, I could say in 1 meter, I have 100 centimeters, and I would cube that. Either one of those is equivalent, right? And you'll get the same answer. This makes a little more intuitive sense to me, that I say, I know there are 100 centimeters in a meter. And you probably know that too, right? There are 100 centimeters in a meter. 100 of those little numbers on a meter stick. Uh, but this doesn't really make intuitive sense to me. I mean, I understand what it means, but this makes more sense to me. So usually I'll write it this way. I'm sorry if that confuses you. Does that confuse you to no end? Okay, good. Uh, Either one of these is equivalent. And if I do this calculation, 5.7 times 10 to the third divided by 100 cubed, you try that out. 5.7 times 10 to the third times 1 over 100 cubed. Somebody tell me what they get with that. Can you give it in scientific notation? No, that's not right. No, it's not 3. I don't think. Oh, yeah, it is 3. It is 3. You're right. Negative 3. All right. Um, Let me show you something on your calculators, okay? A lot of you have TI, so let me pull up a TI. Get a good image. Let's see. This will help you out a lot as you're working through problems, and I find students make this mistake a lot. That's not what I want. Sorry. Okay, whenever you're doing these things like, say, 1 times 10 to the minus 3, or 10 to the third, which is what we were just doing, press the button. If you want to do that, let's say I want to do this 1 times 10 to the, what were we doing? We were doing 1 times 10 to the third, is that right? 10 to the third, 1 times 10 to the third. The easiest way to do that is to hit your 1 button right here, and then do the second EE right here. And what you get on your and then do 3. What you get on your calculator then, you'll get 1 E 3. And that's the same as 1 times 10 to the third. I know that a lot of you instead will do it this way. And you're really inviting problems on exams because if you don't get your order of operations right, it won't work correctly. A lot of you would do it this way. Besides the fact that there's just more numbers that you have to hit when you do this, if you don't get your order of operations right, it's not going to give you the right answer. So I really recommend that you get in the habit of anytime you do scientific notation that you use this E button, which is right here. You have to do second EE. If you have a TI, even I think on these you have that. Is that correct? Yeah. All right. And if you have a Casio or some other calculator, you probably have that button. It might be in a different place. Okay. Are y'all familiar with that exponential button? Most of you are, but some of you are not. And I've encountered a lot of students, and they make mistakes on exams for this reason, that they get their order of operations wrong, and if they use that E button, it really dispels that problem. So from henceforth, always use that button for a scientific notation. Can I get a pledge from all of you? Henceforth, I shall use that button. I don't know what it's called, the E button. Okay? Great. Okay, we can also have unit conversions just between, you know, whatever. Let's just say I make up this unit, 364.4 smoots is 125 meters. So let me see if I have the clip for this. I'm sorry, I do not have it. Doesn't matter, it's not that important. Um, and let's say I want to know how many smoots is in 225 meters. So here I'll just do like I've been doing. I'll say 225 meters. Here I have a unit conversion factor. It's a little bit different than what we've been doing, but I have 125 meters in the denominator and 364.4 smoots in the numerator. It's just a unit conversion factor like we've been doing. And then I can convert these meters to smoots, this imaginary made up unit, and I get 656 smoots. Right, likely what you'll see in the exam are conversions of units with powers, like that where we had to cube the conversion factor, like we did before. You can look in the homework, there's some sample problems, and then also on the old exam, some more practice for you there. Okay, you with me on this, okay? Yes? All right, hang on, we just have about, what, 15 more minutes, I think. All right, oh, we have 5 minutes? Okay, thank you, Ainsley. Yeah, we get at 8:25. Okay, students often have trouble with this. Estimates and order of magnitude. In this, we're going to be comparing known physical quantities, things that we know the measurements of, to things that we don't know the measurements of. So for example, I might ask you, what is the area in square centimeters of your sheet of paper? Or what is the volume in cubic meters of this room? And in order to answer those questions, you need to know two things. You first need to know what are those basic SI measurements. You need to know that a meter is about this long. It's about 3 feet. A centimeter is about how big? Very good. It's about the size of your pinky. All right, everybody hold up your pinky. I can't see them all. Hold them up a little bit higher. Yep. All those are a centimeter, roughly. All of your pinkies are about 1 centimeter wide. Okay? So look at your pinky and say, huh, I didn't know that that was a centimeter. Go ahead. I didn't know that that was a centimeter. No, seriously. All right, go ahead. I didn't know that that was a centimeter. Thank you. Thank you. Yeah, so this is a centimeter roughly. And so if you need to know the width of your paper in centimeters, you can just use your pinky to estimate that. Okay? A kilogram is between about 2.5 pounds, right? So a person is roughly how many kilograms ish? 70-ish, 70 to 100, right? And so you need to know those physical quantities. I won't have you estimate a time, but I will have you estimate area, volume, or mass of something. All right. You also need to know how to pick out answers that are incorrect. When we call order of magnitude, that means to within a factor of 10. Astronomers do this a lot, right? Like we don't really want the right answer, we just want to within a factor of 10. So you'll be looking for answers that are to within a factor of 10. So say for example, what is the volume of this room? Can y'all throw out some numbers what you think the volume of this room is? How wide do you think it is roughly in meters? Is it 1 meter? Is it 10 meters or 100 meters? It's pretty darn close to 10 meters. So we're just looking for rough order of magnitude. So it is about 10 meters. In fact, you can count the tiles, right? The tiles here are 1 yard apart, which is about a meter. It's about 10 meters. If this is 10 meters, what is the depth or what is the length of the room? Maybe 20. So what's that? Okay, let's just say 20. So it's about 20 meters long. All right, so is it 2, is it 20, or is it 200? We'd say it's about 20 meters long. And then the height of the room, yeah, about 2 or 3. We'll say 3. So we have 10 across, 20 back, 3 up, right? So just as a quick estimate, we can say that the volume of this room is 10 meters by 20 meters by 3 meters, roughly. And so that's going to be 200, that's going to be 600 cubic meters. So on a multiple choice test, I could say, is the volume of this room 6 cubic meters, 60 cubic meters, 600 cubic meters, or 6,000 cubic meters? All right, and you'd have to pick in the right answer. Okay, and obviously it'd be 600. If it were 60 cubic meters, like one of these would have to be off by a factor of 10. If it were 60, it would be 10 by 2 by 3, like a room about this width all the way, or excuse me, a room about this wide, right, if it were 60. But instead it's 600. Follow me? You need to pick out those answers that are obviously wrong by looking at the order of magnitude. And 3 answers will be obviously wrong on those things. We're not going to do the pages in a book. I'm just going to skip that. Let's try this one. What is the area of the projection screen at the front of this room, this screen right here, what is its area? Is it 1 square meter, 10 square meters, 100 square meters, or 1,000 square meters? 3 of those answers are obviously wrong, okay? Just looking at doing order of magnitude estimates. I have a good joke for you if you get this one right. Like, if we get above 90% right, we will, I'll tell you the joke. So if you're not certain, you can ask your friend, you can ask your neighbor what they put, you can look in your book, you can use whatever resource you want. You can call somebody on your cell phone and like take a picture of this and send it to them. All right, I'm going to stop at 105, 105. 83%? Sorry. But B is the right answer. A 1 square meter screen would be a 1 by 1 meter. So it'd be about this big, right? Uh, a 10 meter square, that's about 3 by 3. That's about what this is. It's about 3 by 3 meters. 100 meters squared, that would be a screen 10 meters by 10 meters, 30 feet wide, 30 feet tall. So obviously this screen isn't 100 meters squared. All right, I will go and tell you that joke. Now hold on just a second. Listen, do you know why cows make such great scientists? Let me give you a little joke etiquette. So, like when somebody is telling you a joke, you say, I don't know what. You don't try to answer the question. You don't try to figure out what the punchline is. You just say, I don't know what. Because they're always outstanding in their fields. All right, y'all have a good day. I'll see you on Friday. We'll finish up this chapter. We'll do trig and calculus review on Friday. And then we'll go into chapter 2.